My name is Amy Chen, and I'm Director of Entrepreneurship Programs at NYC Media Lab, where I run the Combine, our venture platform for emerging technology startups. Many of our startups come from the universities here in New York. Many of them are spin-outs out of university R&D labs, and we also run corporate entrepreneurship programs. I've been with the lab since 2014, and it's been fantastic to convene our community for this conference every year, so we can highlight the trends and dive deep into discussion on the key technologies that are affecting the way we consume, produce, share, and distribute media and information. Hope you're all enjoying the morning so far. We had a keynote discussion on AI and competition, as well as a panel on AI and media. Now we'll showcase what's state of the art, so you can get a sense of technical R&D from the experts in university and industry labs. We've got a great lineup in this session. I will introduce each speaker, and we'll have technical presentations, about 8 to 10 minutes each. After all the speakers have presented, we'll have a Q&A here on stage, and then I will also invite audience Q&A, so please save your questions for later. I'm pleased to introduce our first speaker. His name is Shih-Fu Chang. He is the Richard Dicker Professor of Electrical Engineering and Computer Science at Columbia University. He leads the Digital Video and Multimedia Lab at Columbia Engineering, where he also serves as the Senior Executive Vice Dean. He is globally known for his research contributions in image and video search, multimodal knowledge extraction, and media forensics. His research has led to several startups and many licensed technologies, including a video intelligence startup called VidRover, which graduated from our NYC Media Lab Combine Accelerator and is currently backed by Techstars, Samsung Next, and other institutional investors. Let's welcome Professor Chang to the stage. Today, he will share his latest research on knowledge graphs.
So is there a control or just press? Sorry about that. Okay, so I think we can start and we can just move the slide over there, right? Or you have a clicker. Okay.
That's the clicker on the table?
Could be. Thank you. All right, let's try this one. I'm Shih-Fu Chen, a faculty member at Columbia University, has been there for more than 20 years. And yesterday we have our 265th graduation ceremony. Wonderful, 60,000 people on Morningside campus there. Engineering school, we have grown a lot. So far has 200 and almost 30 faculty members and hired 90 faculty members in artificial intelligence, machine learning, data science area. So a lot of people, we invest in AI and media. So today I'm going to talk about more on knowledge graph. You have heard a lot about knowledge graph, and I'm going to focus on so-called multimodal knowledge graph there. So I think any number you see here about the data on internet probably is already out of date. And my student across some of the number here, every day we see a lot of news article being uploaded to maybe news site or blog site. And then there are even more pictures being uploaded and video minutes uploaded. So the question here is, given such tremendous amount of data, how do we extract information or so-called knowledge or value from that data? And there's a lot of interest in so-called natural language processing to understand information in text. So let's construct the information graph or knowledge from a text document. For example, if you have a set of documents here, and you have the sentence or description or narrative talk about what happened. And it's not only talking about, okay, which word happened, which name was mentioned. Can we construct a graph to abstract, to really summarize, okay, who and what and why and how? For example, here, triangular indicates the event that really happened. So in this sentence, Prince William visited Israel. So there is a visit event. So this is the event node here. And then you have an entity who is the person paying the visit. And then you have the location or the destination the person visit there. And one by one, if you can construct this kind of entity and structured relation, then you have the information about the relation here and the knowledge to capture really what happened. And not only one event, you also have a multiple event mentioned in this paragraph here. He visited Israel, and then he's going to have a meeting with a leader in that region. So you have a meeting. So that the relationship between the event is also very interesting in summarizing what's really happened in the real world. Once you have this kind of a so-called knowledge graph, so now you understand what I mean by graph. You have the node, you have a relation, you have the structure. Then you can expand the graph by augmenting information we already accumulated or narrated in a knowledge base such as Wikipedia or other locations there. Then once you have this expanded knowledge graph, then you can answer questions, right? The question come in to say, find the reason visit by politician or royalty to this region for maybe for different purpose, and then see what happened. And then you can have some kind of automated fashion trying to infer or trying to reason based on the graph to answer the question here. So this is great. I think this is a very exciting area. But now the question is, can we expand this to multimodal? And remember the number I was showing here, 3 million news articles per day. But you have 300 million photos per day also to upload it. And you have 25 million minutes video. What do we do with those visual content? So can we extract similar structured knowledge graph from the visual data? And why do we need a multimodal? Just give you some example here. Visual data augment the information in the text document by illustrating really what happened in the real world. And second, also by providing evidence to disambiguate that might be originally ambiguous information. And also by providing additional details. For example, both texts mention modern baseball. Without a text, without a picture, unless you are expert or maybe you're familiar with the domain, you probably need some help from the visual evidence to help you, or at least to help the machine to disambiguate what this mention of the modern baseball actually mean. And the other one is to provide additional details. In this text narrative, we mentioned there's a group of protesters performing an attack event on a target bus and carrying certain supporters on their way to a rally, and so forth. So by analyzing the text, we probably can construct a knowledge graph to say what happened. There's a rally, there's a protest, there's an attack. But visual content provide additional details to tell you exactly how that attack event was happening. For example, if you go back to the knowledge graph, you have an event called attack. You have an attacker, and you have the target. These are all readily available, extractable from text document. But visual content tell you additional information, what is the instrument actually used for the attack. So the goal is to construct this multimodal graph, knowledge graph from multimodal documents. And that can be have a series of a document in the video, in the blog, in speech and audio speech recognition. And at the end, this knowledge graph can be used to answer the question, to reason, to infer what's going to happen, to do prediction. And very quickly, I think I only have a few minutes left, very quickly to see what are the research issue we in my lab is addressing, and there are many experts here. I saw several familiar names also attacking in this field. And this multimodal knowledge graph research is happening in multiple communities, not only in computer vision, in AI, in natural language processing. It's really encouraging to see people from different disciplines actually working together in this area. And very quickly run through a few research challenges we are working on. One is parsing structures. Second is to do grounding. Third, name entity recognition. And last is multimodal argument rule. The first one, given the pictures, I think 10 years ago, 2012, since the deep learning took over the object recognition, now the machine can recognize tens of thousands of objects in image and video. So that's what happened in the last 10 years or maybe 7 years. What we really want to drive the frontier is to the next stage. Can you construct the graph relation structures on top of the entity you can recognize. So you see a person, you see a bike, you see a building. What is the relationship? What's the structure? What are they doing? So that's one of the aspects that's of the computer vision and AI is trying to drive the advance. Can you parse image video into semantic structures? So there's a lot, if you can do this, then a lot of application, reasoning, question, answer, common sense, right? Once you have enough knowledge graph, then you can infer what is the common sense that exists in the real world. So very quickly, one example here. I'm not going into the detail. One of the paper coming up next month in the CVPR, we have a new tool called Visual Semantic Parser. They can take an image, parse the image into objects, understand what is the object, so person, skate, helmet, bike, and also automatically find out what is the relationship between the object in a very efficient way. The second problem that's actually motivating our research is grounding. So the first challenge is structure. Second is linking. Can you link the structure in text to the visual objects? For example, if you have a narrative, say, there is a crowd of onlookers looking at tractor right, and you have the pictures here. Can you do a specific linking of the phrase mentioned in the text to the object in the pictures? And this is complete the goal of a so-called multimodal graph I mentioned at the beginning. It's not only recognizing an object here, not only constructing the structure here. You want to do a detailed linking between the entity in the text and entity in the pictures. If you can do this, then you can do hyperlinking to local visual object in a very fine-grained way, and you can do information augmentation. And so one of the paper is coming up again next month. We are using a so-called multimodal common space learning at a different level, different granularity, to do the grounding of every word mentioned in the text to every possible object in the picture, to ground the mention of the text and object. And there are some benchmark evaluation right now. People are comparing different performance. The third challenge is actually an old problem, but is very important in this kind of multimodal knowledge graph. It's particularly related to name entity. It's not only about a bicycle, a car, a building. It's the name entity. Name entity is a name person, name building. For example, this is a Bloomberg building. It's not only a modern building. Specifically, you want to know where that is, who is that person, what is happening. So it's called name entity. You can run face recognition to recognize people's and then their identity. But a lot of time when you do streaming or new application, you don't really have a predefined database for you to train the face recognition model. So if you encounter the new faces or new name entity, how do you use multimodal document to infer possible name of that person? For example, this picture has a caption mentioned 2 possible names of 3 faces there. So which one could be the possible name for each of the face? So it's called unknown open vocabulary, open set face recognition problem. So using the multimodal capability, you can look at the co-occurrence between the possible name and the face identity, and then you can try to look at the face similarity. And after that, you look at the so-called bipartite clustering. You'll be able to figure out what is the possible name assignment. For this one, you assign to Juno, and this one, you probably assign to Vanessa. So by looking at the multimodal name entity recognition. The last challenge I'm going to mention is argument role recognition. And this is a specific problem in NLP trying to understand who and which entity participate in the event. For example, in the sentence here, if you parse this sentence, you mentioned there are 2 events here, one die, one attack, and you can understand what is the argument involved in each event. Having a multimodal document, you can parse that too. Police detain a protester in Moscow. Then you say this is an event, this is an agent, and that's a patient. And that's the entity involved in the event. But if you look at the picture here, there are additional arguments mentioned in the image that's not mentioned in the text. Can you recognize the additional role played by a visual object in the event that's not mentioned in text? So this is a very interesting problem people are working on. So I think I have 2 slides and I'll finish. So having all this, what is the application we're looking at? One, we're looking at question answer. Remember this IBM Watson that's competition. You look at the question, you answer here. Look at the picture. Can you answer the question like this? What is the person going to do next? So this is some of the challenge that we are embarking trying to answer. Not only recognizing there's a person, there's a fish tank, or there's actually machine make a mistake here, mistaken the fish tank as a wine glass. You can see the technology is still not perfect. But given this imperfect recognition result, can you answer a question that requires some reasoning? It's not only answer the question, how many people in the picture? What are they trying to do? What is the purpose of this gathering? So to answer this question, you have to be able to create knowledge graph, and you have to be able to infer some common sense knowledge. The second application we are actually working on through the Media Lab sponsorship with Hearst is generating this knowledge graph from multimodal document. At the end, you can work with a different target user and then create a new edited video with the narration for different story generation. So, conclusion slide. My message is computer vision, NLP, AI, machine learning are working together towards a very exciting goal of a knowledge graph construction. And every modality helps, and there's a lot of challenges there. And there's even more challenges that can machine learn common sense through this process by understanding the common sense related to physics, behavior, affordance. For example, we all know this cup and saucer is used for filling coffee, but if you knock over the cup and saucer on the ground, it's going to spill. This is common sense. Can machine learn this? We know if you step on a banana peel, it's going to fall, it's going to slip. Can machine learn this? We all know my last slide, after conclusion, I have to stop. Then can machine learn this common sense? Okay, thank you.
Thank you, Shih-Fu. Our second speaker will be Shioulin Sam, who is a research engineer at Cloudera Fast Forward Labs, where she bridges machine learning, academic research, and industry applications through consulting. Many of you might have heard of Fast Forward Labs, which was acquired 2 years ago by Cloudera. Before joining Cloudera, Shioulin managed a portfolio of early-stage ventures focusing on women-led startups and public market investments. She also worked in the investment management industry designing quantitative trading strategies. She holds a PhD in electrical engineering and computer science from MIT. Let's welcome Shioulin to the stage to share her research on machine learning with limited labeled data.
Good morning, everyone. Can you hear me? Yep. Thank you, Amy, for the introduction. So I'd like to start by just telling you what we do at Cloudera Fast Forward Labs. The goal at Cloudera Fast Forward Labs is to bridge the gap between research in machine learning and industry applications. And one of the ways we do that is through publishing research reports. These reports are meant to highlight an emerging capability within machine learning that we believe will become important for the business community within the next 6 months to 2 years from when they're published. Here are all the reports that we have done in the past. They might seem random to you, but there's a reasoning behind these topic selections, and we can probably go into that later during the panel discussion. But today, what I would like to do is focus on the latest research report that I led, which is on learning with limited labeled data. I'm only going to go through a very high-level discussion, and I will share some resources later on if you're actually interested in learning about the technical details. So, supervised machine learning is powerful because it lets us teach machines using examples. But those of us who work with data know that real-life data doesn't always come nicely packaged with labels. It is messy and unorganized. We might have a lot of data, but it's actually very hard to leverage them to build anything useful for the enterprise. In financial institutions, for example, risk assessment is crucial because that determines the amount of capital that needs to be put aside to absorb systemic financial risk. Volumes and volumes of loan documents and contractual documents exist, but not very many of these have actually been annotated to extract information such as loan ID, loan type, loan purpose, collateral amount, and so forth. In healthcare, tons and tons of medical images exist and can be used to build a diagnostic model. But once again, not very many of these images have been properly annotated. In corporate IT, chat logs are available and are actually very useful for companies to understand customer preferences and customer satisfaction levels. But these logs also need to be annotated to extract information such as product ID, product type, customer concerns, and sentiment, and so forth. So what should enterprises do to leverage this type of real-life data? One approach, which is a manual approach, is to just create labels for everything. Now, this is very time-consuming, and it's also expensive and inefficient. So there has to be a better way. Can we use some kind of intelligence to select what to create labels for? Can we actually just select the data points that are helpful for the machines? Can we actually build a machine learning model using a small set of label data and have it perform almost just as well when you compare to a model that we would have built using the much larger label data pool? So it turns out the answer is yes. With active learning, you can take advantage of the collaboration between machines and humans to smartly select a small set of unlabeled data to create labels for. You can then build a machine learning model using this small set of labeled data. This opens up new product possibilities previously constrained by limited labeled data and actually allow enterprises to leverage their large pools of real-life messy data. So let's take a look at how that works. You start at the top left-hand corner with a small amount of labeled data. You then take this to build a machine learning model. The model then is used to make predictions for your entire pool of unlabeled data. Now, in the process of making prediction, the model also identifies points that it has the most difficulties with. These points are sent to a human. The human provides the label. That data point now becomes a labeled data point, and we add it back to our original labeled data pool, and the cycle repeats. At the heart of active learning is the learner's ability to label smartly. Now, what does that mean? The learner has to be able to pick out points that is difficult. It turns out the learner relies on strategies to help surface these data points. I'm going to use a simple example. So assume we're building a model to predict product reviews. We want to classify reviews into positive or negative reviews. And we have a very simple model that gives us a linear decision boundary shown in pink here. And we only use two features, the number of positive words and the number of negative words. Now, all the data points to the right of this pink line are considered positive reviews, and the ones to the left are considered negative reviews. The data points right around the decision boundary are the ones that the model is most uncertain about. Any small changes in the decision boundary, for example, changing from the solid pink to the dotted pink line, will cause these same points to be classified differently. But data points very far away from the boundary are safe from these changes because the model is very certain about them. So in active learning, what we do is then compute the distance between a data point and a decision boundary, and then we pick the data points that are close to the decision boundary to get labels for. Knowing labels for these data points will help this model become better as it refines itself. So in all our reports, we also build a prototype to demonstrate this particular capability. I'm just going to show a video. The idea behind this prototype is to build a tool that allows you to understand why and how active learning works. And we do it using 3 data sets. On the top here, you would see 3 data sets, MNIST, QuickDraw, and Caltech. The MNIST data set is the Hello World data set of machine learning. It is a series of images of handwritten digits from 0 to 9. The QuickDraw data set is slightly more complex. It is a series of hand doodles of objects like apples, oranges, broccoli. And the last one, the Caltech data set, is most complex. So this is an example of the QuickDraw data set. You see like doodles of apples and broccolis. The Caltech data set is most complex. It is a series of real-life images. So what we do is we take these 3 different data sets and we apply different selection strategies. On top, you'll see 4 strategies. One is random, which is the baseline. In random strategy, you kind of just randomly select things. And the other 3 are more complex. The entropy is based on uncertainty. And the last 2, the adversarial and the ensemble, are based on strategies that work for deep learning. So the idea behind this prototype is to essentially look at how active learning works with different types of data set, and how data points are selected. Are you able to repeat the video? Yes, thank you. So you'll see that these are the MNIST data sets, and you see the blob in the middle are just clusters, and the gray dots are actually the points that the strategy has surfaced to request labels for. So for the MNIST data set, the original data set has 60,000 labels, but for this purpose, we only assume that we have 5,000 data points that has labels. We build a model using the 5,000 labeled data points. We ask a strategy to select the next 1,000 unlabeled data points to create labels for, and then we add that additional 1,000 to the original 5,000 labeled data point pool. Now we have 6,000, and we repeat the cycle. And you will see that as you add more data, obviously via active learning, the performance gets better. And we don't really need to use all the available data. We only needed to use about, I think, 18% of the data to get accuracy of up to around 98%. So this is publicly available. If you are free after this panel, feel free to play with it. Now, what are the use cases for active learning? Active learning lets us build models using less labeled data, and it lets us build it faster. But it requires a human to actually create labels for these data. So active learning is most suitable for use cases where the data comes in the form of text and images, because these are the data types that humans can create labels for. And in addition, active learning is most effective when you have too much data, such that the labeling cost is enormous. With active learning, you can greatly reduce the number of labels you require, but at the same time, you can actually still build a model that performs quite well. So in all these examples here, autonomous driving, the status quo right now is to just blindly create labels for everything. These projects, labeling projects, start in the low six figures and go up from there. But it turns out a lot of the data that's being labeled are actually not very useful for the model. So with active learning, we can just pick the ones that are helpful, create labels for those, pay for those, and only use them. In medical diagnosis is the same scenario. There are a lot of images that need to be labeled, but in addition, the labeling cost is very, very high. You need a domain expertise to create labels for each of these images. It takes a long time, it's very expensive. So why don't we try active learning? Product recommendations and customer inquiries are two text-based use cases. In these use cases, you generally have a lot of information. In product recommendations, you have a lot of a lot of feedback that customer has left you. But unless you can actually turn these feedback into labeled reviews, you can't really use them for product recommendations. Customer inquiry is the same. Customer inquiry comes in and they need to be routed to the right department within an enterprise. And that is often the bottleneck. But we can obviously build an automatic router. But to do that, we need to actually have labels for all these inquiries. And instead of building labels for everything, you can start with a small set of labeled data and then kind of build on top using active learning. Here are a list of resources that I promised. The prototype is publicly available. You can find it at activelearner.fastforlabs.com. We also have a series of blogs on our website, blogs.fastforlabs.com. There is a guide to learning with limited label data, a visualization story, and an invitation to kind of play with it a little bit. And if you're interested in the technical details of this talk, I did a recording with Twimmel. You can find it on their website. And that goes into a lot of details of why active learning doesn't work for deep learning and how we would actually adapt it or change it such that it would be more effective. And that's it I have. That's all for today. Thank you.
Thank you, Shioulin. Next in our lineup, we have Naaman, Associate Professor of Information Science at the Jacobs Institute at Cornell Tech. I'm curious, who in the audience has visited Cornell Tech? It's a new campus on Roosevelt Island between Queens and Manhattan, just over the bridge or a tram or subway ride away from here. At Cornell Tech, Moore is the founder of the Connective Media Hub, and he leads a research group focused on topics related to the intersection of technology, media, and democracy. The group applies multidisciplinary techniques from machine learning to qualitative social science to study our information ecosystem and its challenges. Previously, Moore was on the faculty at the Rutgers School of Communication and Information, led a research team at Yahoo Research Berkeley, and received a PhD in computer science from the Stanford University Info Lab. He's also a former professional basketball player in Israel and a former startup co-founder. Moore, we're looking forward to hearing from your research on computer vision today. Come join us on stage.
I don't use my height as frequently in this business as I did before. Cool. So yes, I was just across the river at Cornell Tech. So you walk down this street and take the tram, and you're right there on the island. But I'm here to talk about AI and a little bit about how we use AI to support the journalist's workflow in the context of misinformation online. You already heard multiple times today that AI is not just here to help us, it's also here to get us. And in particular, AI, as we've all seen, is increasingly capable to generate realities that look very hard for humans and for machines to discern from fake realities that are hard for humans and machines to discern from real ones. To mention just a few recent examples, most of them happened since we had this event last year. We now had, this is work from NVIDIA, showing how they can generate fake humans, essentially, using a deep learning technique called style transfer that are very, as you can see, very convincing, but entirely fake. We have, this is Lyrebird, where they synthesize voice based on any text to any human voice. In this demo, they have Obama, Trump, and Hillary discussing their excellent platform. Everybody's seen this is from last year. I think we talked about it a lot here in this event, where Peel is using his own voice, but AI renders Obama's movements and lips to match the content that Peel is saying. This is one of my favorites from last year. This is called Everybody Dance Now. Sorry, now stuck a song in your head for the rest of the day. This is from UC Berkeley, and they take any source video, detect the pose and the movements, and transfer it to an actor. This is only done now in studio lab settings, but in the future could probably apply to any type of capture. And also in text. This is from Ben Zhao and the group in Chicago, where they use RNNs to create entirely fake but completely believable product reviews trained from real data, but and tested on humans. So how do we fight back? The AI arms race will be hard and cannot easily be won. Maybe we can discuss why a little bit in the panel. But in one project that I'll briefly present today, we use collaboration and AI to address some of the challenges, especially in the context of misinformation. So in particular, in this project, we use computer vision to support workflow around misinformation. So imagine very quickly a journalist that encounters, it could be a fake image or an image that's out of context or an image that was generated by AI, and they're trying to verify that. The expert will do a lot of steps. They'll do Google reverse image search. They'll go to specific interfaces that are meant for them to analyze the content deeply. They'll look at the shadows and the weather and all that stuff. Very few journalists around the world are capable of doing this deep work today. But even once they do and maybe decide that this image is fake, out of context, some other issue with it, the journalist in the next huddle over might ask the same question about the same image, not knowing that that another person has already done that. And this is not just true in the same newsroom. Apologies, I think I'm showing the Times newsroom. Should have adapted my slide. it happens in newsroom around the world that are all probably encountering that image, maybe in the context of a breaking news report and trying to verify it. So some of these are fictional, as you notice. So here we use some advanced computer vision and deep learning to enable this collaboration around the images. So we're using the image as, well, it's not a URL because we use the image as an identifier as a key for other journalists looking at similar or modified images that look like the one they're viewing right now to understand what's going on. This is a slightly larger project. Part of it is streamlining the reverse image search. That's to do it better than what Google provides right now. Part of it has to do with indexing and searching social media resources. That if you're a journalist, if you search Google for images, they are understandably not going to show you results from Reddit and 4chan and other sources of misinformation for good reason. But journalists often want to scan those sources. But in particular, I'm going to talk about supporting the image annotation collaboratively. So the idea here is that we have one journalist that may do the verification or de-verification, and other trusted journalists, maybe in the same organization or the same consortium, can see their notes regardless of where the images appear and also whether that image has been modified in some way, which is where our computer vision comes in. So just a quick sketch. This was made by my master's students in a tech media and democracy class. The interface that sits on top of it. Say you look at an image of Trump landing on the moon, or representatives. You can click the link of inspect, and then you can either check what other people reported or see what other people reported for that image, or add you comment yourself. And whenever anyone else looks at that image, there will be Chrome extension in their browser that will give them that information, whether or not they're looking at exactly the same piece. This is kind of what it might look like. So just to make clear, this is not AI fighting AI. We're not necessarily creating a tool to tell you, oh, this image has been doctored, this image has been modified. This has a lot of nuance in it. What we're providing here is a technique to find those similar images, regardless of change, to support collaboration. In particular, some of the techniques we're developing, hoping to be able to address some of the challenges, some of the things that may happen to an image. For example, adding visual markup, changing colors, cropping, all the things that people might do to avoid detection or in the natural course of editing and publishing images. A couple of computer vision slides. This is actually an older technique. We're using a technique called ORB that extracts visual features from the image that are kind of geometric features where we can compare one photo to another and find the relevant areas and then decide whether or not they're a match. We're also using the deep learning techniques to extract from the VGD network, extract a set of features so that we can then compare and index to find similar images. This is all then extracted from images using the face search index from Facebook, a package that's available from Facebook to then search in real time images that we want to query. So very quick summary. We have AI-generated content that is increasingly real, and we want to use AI to propagate the outcome of the expertise-based content evaluation to others in our trusted network. This is just one of the projects in our lab. You can ask me later, maybe we can talk in the panel about our work on trust, generally trust in online environments, including what happens when AI is involved in producing content and how trust changes as a result. Thank you.
Thank you, Mor. Our final speaker in this session will be Gary Kazantsev, Head of Quant Technology Strategy from the Office of the CTO here at Bloomberg. Gary is the head of engineering machine learning here, leading projects that intersect computational linguistics, machine learning, and finance, including sentiment analysis, market impact indicators, machine translation, text classification, information extraction, and predictive modeling of financial markets. Gary is involved with advisory roles with fintech and machine learning startups and has worked at a variety of technology and academic organizations over the last 20 years. Today, Gary will share with us a live demo from the Bloomberg terminal. Gary, welcome.
How much time do I have? Second. Right. Can everybody hear me? Okay, wonderful. So my talk is going to echo a lot of what was said earlier. Right? So these are the news stories that we ingest. Right? A lot of what I'm going to say is in context of this picture. So when I started here about 12 years ago, we ingested about 250,000 news documents per day. Today, we ingest on the order of 2 million, maybe 2.5 million. So I think it's about, 80% of the 3 million that Professor Chang mentioned. So we have a little bit of ways to go. From about 125,000 different sources in 40 different languages, right? Suffice to say that this is more content than any human being could possibly read. Right? This is some random Thursday. On Monday morning, this scrolls by so fast that you can't even see it. Right? Now, in a way, we are victims of our own success. Right? Clients asked us to get our hands on all the news stories in the world, which we did. And then they came to us and they said, well, we can't read it all. Right? So how do you make sense of this? Right? Well, you start by doing things that were mentioned previously. So things like entity recognition and topic classification, right? And then that enables you to do things like this. So this is showing a couple of different things at once, right? So this is a result of a fairly deep NLP pipeline that does recognitions of entities for companies and people, locations, industries, people, and so on and so forth. So this is a result of approximately 200 man-years worth of work, give or take. You can do a lot of stuff with the system once you actually have these annotations. Right? So I think this is the only system in the world that I know of that will correctly interpret the word Hillary, because it could mean a lot of things, right? But because Trump and Obama are both either presidents or ex-presidents, it will understand that Hillary refers to Hillary Rodham Clinton, as opposed to some other thing or person named Hillary, right? Now, I'm jumping ahead a little bit, right? Because this is kind of supposed to be about topic classification. Now, once you have this, right, you can do a lot of other cool stuff. You can produce counts, right? You can do things like this. So, amount of publication by company, right, or by topic. This tends to take a little while. This is actually real time, right? You can build this system on top of other things. So, for instance, if you wanted to know how many stories were published about the topic of terrorism since 1990, you can get it for the price of typing it in. Right? This usually takes approximately 10-15 seconds because this is actually crawling over 30 years worth of content. Right? But you can do hypothesis testing essentially in real time by typing in queries. Now, once you know these things, such as what the story is about, then you can ask more complex questions like, is this story positive or negative? Right. You can ask this about news or social media. You can ask questions like, is this story going to move the price of some particular security? So this picture is actually very expensive to draw, right? Because if you think about it, this is one of those cases where annotation is very, very expensive. Echoing, again, an earlier talk. Because you cannot ask humans if this story is going to move the price of some particular security, because people just don't know. Even the people who actually wrote this story. Right? People just don't agree on that type of thing very frequently. So what you need to do is first run an anomaly detection system over all the intraday time series. So a big name like City generates somewhere on the order of a gigabyte of ticks per day, times 20,000 actively traded securities, times 220 days in a year, times 10 years, you very quickly get into very, very large numbers. So just to draw this picture, right, is a non-trivial problem, just in terms of electricity costs, right? And then you associate news stories to all of these spikes, and then you have to have humans annotate those, right? And then you end up with tens of thousands of pictures like this, on top of which you can actually build a very powerful predictive model which will look at news stories as they come in and say the probability that it will move the price of this particular security is X, something like that, right? Now, in the beginning, I was showing the question answering kind of stuff, right? You can do that for a number of different things besides news stories, as you might imagine. So, for example, how many people are Bloomberg users? So not many. How many people who are Bloomberg users know how to draw that chart?
Yeah.
Okay, one. Boy, you can do this. Again, this does entity recognition and semantic parsing and a bunch of inference to actually understand what these things mean, right? This is not limited to just stock things. If you were interested. You can ask questions like this about people and companies. Well, suffice to say that without the Bloomberg terminal, to answer this question will take you approximately a month. Right? But even on the terminal without this functionality, it would take you a whole bunch of clicks. Right? You can find out exactly how many clicks, actually, because since we have the actual semantic interpretation of this, right, we can decompose this query into what the actual structured query might be. Right? So this is all built on top of a very involved natural language processing pipeline, right, which does this in multiple languages in real time, right, across all of the 2 and change million news stories that we ingest per day, right? But we can go further with this sort of technology. A lot of talk nowadays in journalism is about automation. So all the stories on the screen were machine generated. Right? We do more and more of this. You can see that these stories are fairly diverse, right? And the number of them keeps growing. Right? Now, this is kind of inverting the problem, and from understanding, right, we are now moving towards synthesis. I think this should give you a fairly broad overview of the types of things that we apply machine learning to at Bloomberg. This is only scratching the surface. Behind every one of the screens that I showed is an academic talk, approximately an hour in length. So if you have any questions, I will be happy to answer them in the panel. Thank you very much.
So thank you all for sharing your research. I'd love to ask a few questions. I think the technologies have really advanced over the past few years. So I'd love if each of you could share, what was possible just a few years ago with what you demonstrated, and, how has this become so accessible to people like you to build prototypes to show these use cases so easily? Whoever would like to start.
I can start?
Yeah.
So I'd like to start with a very high-level description of how we actually pick topics for our research reports. We use 3 criteria. So first, the breakthrough that we're looking at has to be useful. Second, we have to be able to build a prototype to illustrate this particular breakthrough. And third, the prototype or the breakthrough has to be timely, meaning that it has to be more possible now than it was 1 to 2 years ago, and it has to be more possible 1 to 2 years from now. So that's a framework of how we think about topic selection, and I think that aligns quite well with the question. So let's take active learning, the learning with limited label data, as an example. So why do we pick active learning? Active learning is not new, but active learning has only been recently adapted to deep learning. Those classical strategies that I described, the margin sampling approach, is classical because it doesn't work for deep learning. So recently there has been a bunch of papers that came out that kind of explains or translates or rethink all these heuristics such that we can apply to deep learning. So that's one of the reasons we decided to write about it. And the second reason is active learning is a change in the workflow. So the human needs to come into the loop. How do you make that happen seamlessly? Currently, if you're really just doing research, the data scientist can just label a bunch of samples and then retrain using the active learning loop. But if you're actually making a product, this needs to scale. Even though we need less data, but the data is still significant, the number of labels that need to go in is still significant. There has been a lot of companies that popped up recently that provide platform access. So you can easily load up your data and then the labels will come in through the platform, and then that will allow you to loop in this process seamlessly. So those are some of the two things that we think about as we write the report. So this wasn't possible a couple of years ago, but it is possible now because of the supporting ecosystem and the supporting research. Another example that I'd like to give is in transfer learning for languages. So the ability to understand language is always something that we would love for computers to be able to do. Now, computers can understand images because of transfer learning. When I say transfer learning, that's, for those of you who are not familiar, that's ability to use a pre-existing model for your own data. So you don't need to bring in a lot of data. You can just bring in some data and then kind of fine-tune the existing model. And because we're able to transfer learn using images, the image analysis kind of exploded in machine learning and AI applications. But that was not possible for languages for various reasons. You cannot transfer learn language models. But this has changed since the end of last year when a slew of paper came out that allows transfer learning. So there are now existing models that understand context, understand reasoning and meaning of languages that you can take and build on top of using your own data. So those are the two things that transfer learning in languages, and also why and how we think of active learning, things that have changed recently that would allow it to be more possible in the future.
Perhaps from the computer vision side, what was possible just a few years ago versus today?
Maybe I go first and more you can add.
Sure.
So I think last 3 years or the future 3 years, I think as I mentioned in my talk, the most exciting part is really bring the AI or computer vision or natural language processing to a high level close to human. So if you follow some of the blog discussed in AI field, Michael Jordan in UC Berkeley is advocating the next generation AI is a human-centered AI. Fei Li in Stanford is also leading this so-called human-centered AI. And the topic I talk about more, and Xiaomin and others talk about, I think how do you bring the AI tool to be closer to the human need, the human interaction, how they search Bloomberg terminal, and how do you represent knowledge so human can understand the reasoning path. It's not only say, okay, here is a dog, here is a house, recognition is a black box, but you represent the information in a structured way similar to how humans digest, consume, and reason based on knowledge. And there's uncertainty, there's a contradiction. The machine output, as I show in my pictures there, there's a partial error, there's accuracy is not always 100%. So how do you develop an AI system that not just shoot for the 100% accuracy, can you tolerate inaccuracy and then do this reasoning, help human in making a decision making, no matter is in the investment or is a ICU medical field or is a prescription. How do you have a human and AI system working hand in hand in a symbiotic way so there's error resistant there, but then there's a human understandability there? I think that's the most exciting part. I think it's going forward.
In terms of recent development, what enables a lot of it is the commoditization. So just being able, you mentioned 7 to 10 years ago when deep learning started, but now it has been commoditized. So we can use the off-the-shelf packages and TensorFlow, and I mentioned the Facebook face index that can take billions of data points and do a nearest neighbor search and binary field. So all of these are now available that were not 2 or 3 years ago, especially for computer vision tasks. I don't see quite the same wealth in NLP, but I think that's coming soon, partly because the systems are not there yet, but as you mentioned, there have been some recent development that will be commoditized over the next few years, I think, and be made more widely available.
Gary, could you maybe share what was possible 3 years ago here at Bloomberg versus what you're working on now?
Right, so what I showed are things that we built 1, 2, and 3 years ago. Right? Unfortunately, I can't tell you about what are we working on today due to company policy. Right? But you could imagine kind of extending the functionality that I showed in a number of different ways in terms of complexity of content, in terms of languages, right? In terms of depth of analysis, and so on. Right? More broadly, I think what has been most interesting, to me at least, right, over the last 3 years, is the achievement of par-human or superhuman results on a number of tasks. Like game playing in particular is one that has been on top of everybody's mind due to AlphaZero and such, right? But there are, again, on par with human or superhuman results that have been demonstrated in image recognition, in speech, in even medical diagnosis. So we are actually submitting a paper to NeurIPS today, right, on active learning. And I was doing a literature review for it, and there is a couple of very interesting things over the last year and a half, really, right, in particular by Andrew Ng's group on like predicting arrhythmia complications, right, on par with humans, but from just time series. So that was not possible 3 years ago. At least I'm not aware of any work like that 3 years ago. So it's interesting to think about what will be possible tomorrow, but my crystal ball is cloudy today.
Just another question before I open it up to the audience. How do you see that teams within corporations can actually scale certain prototypes that you expose to them? I know, Shioulin, you do consulting, so how are you seeing teams organize around these prototypes and really build workflows to deploy and scale these types of prototypes?
Yeah, one of the common problems that we see in machine learning within enterprises today is that things are not scalable. The data science teams build really cool products, but they cannot seem to get that into production. So I will talk about 2 things that will help that. First, as at the pipeline level, companies need to have a place to gather all data sources, clean it, and allow data scientists to access those easily. So that removes the barrier to getting data. But once you are able to access data, you have to create an environment for the data science team such that they can experiment and fail. Most of the time, these ideas are not going to come to fruition. Most of the time, it's experimenting, it's playing with data, trying to understand what the data is telling you. But you have to create an environment such that they are encouraged to do that. Once that environment is there, a small percentage of these ideas will actually work. That's when you have to have the production pipeline. How do I actually productionize this? How do I scale it? How do I monitor these performance of these models? Because once you deploy them, they start to deteriorate. So this entire pipeline needs to exist before anything can happen. The other thing that we often see is that there is a disconnect between the business and the tech side. You cannot solve technology problems independent of the business problem because they are actually very connected. What data you have access to is connected to your business strategy. So these two sides need to exist peacefully. The business team needs to be active stakeholders in these data science team projects. And the data science team need to be able to communicate back to these business stakeholders. So those are, I think, the two things that we see are currently kind of broken within the enterprise system. But if that gets fixed, we can get to building actual models that are helpful, that are useful for the business use cases, and then actually be able to deploy them and see some results.
More, I think, and Shih-Fu, you might have.
Sure. I think I'm academia, so I think scale up usually is not on my agenda. We get a paper published, but actually it's changing. Many conferences right now even require, when we submit papers, have our code in the open source. NIPS, I think Gary mentioned, as a NIPS conference and others, they require when you submit your manuscript, also you put your data code or so-called reproducible data code in open source. So that's number one. Number two is doing startup. My group, my students started 3 companies in the last 3 years. And one of them actually didn't finish PhD, is still ongoing. and hopefully he will come back. And engineering school, we have 31 companies started in the last 4 years. And this is unprecedented. And I think one way to really to bring the research result to the practical world is encourage people to try entrepreneurship. And the mentality of academia is changing. In the past, when I started at Columbia 20 years ago, entrepreneurship startup was never counted or recognized in the promotion case. And now actually it's recognized very positively. So I think the other way from academia point of view is really just entrepreneurship, right?
I think we actually have a few minutes for questions from the audience, so I'd love to see if anybody would like to ask our panelists anything. Please wait for the mic. Right over here, second row.
Hi, my name is Ulrike. Is this working?
Yes.
Okay. I'm not sure who to ask this question, but it's centered around trust. A lot of media companies, initiatives are rethinking their relationships with the users, and that's based on regaining trust. And I'm wondering, AI, machine learning is already doing stuff in real time, like there's a window that pops up that says, with the likelihood of so and so many percentage, this is fake news or so. You get a little widget. I wonder, is it possible in the near future that this will be taken to the next level? I'm having a scenario in my mind. For example, there's a Facebook group and wild conspiracy theories are circulating. Could there be an AI, a bot that comes in with, fun fact, this is actually not true? Would AI be able to discuss with users and act like a human that way in any time soon?
I think Moore might have
An
answer for you.
That's a very important question for us. Not just the quite a few. This is a very difficult problem because there are humans involved. There's AI involved, and there is the interaction of both. So, first of all, even if AI is capable of detecting it, when are humans receptive to this message, and when they reject it as corporate or the government wants you to think this, and so how to persuade them is a difficult problem. How to extract this and understand this from AI, where we have information systems. So information ecosystem was built, the one we use today was built on the assumption that content that is out there is knowledge and should be retrieved, the results of a query. But this is now no longer true, right? So if you type in something into Google, lemon juice cures cancer, you will get results because somebody put on the web, a lot of people in fact put on the web that lemon juice cures cancer. The basic assumptions of the ecosystems are wrong. So how do we do this with AI? How do we model this information in a way that allows us to evaluate not just whether it's there, but also the veracity, and then counter claims that appear in other places, like conspiracy theories? Very difficult problem, both in terms of AI and in terms of humans. I don't know if anyone has anything to add. I don't want to.
Do you have anything to add?
So I think to a limited extent what you're describing is already possible. In fact, I saw something right very much in line with what you're saying, like, which is kind of like real-time fact-checking, right? Now, when would that machine be able to converse with the human beings in question, right? Opinions on that particular subject vary, and the answers range from sometime in 2050s to never. So I'm afraid we don't know.
Well, thank you. I think that's all we have time for today for this session. I want to give a round of applause to our panelists, and thank you.